My name's WarrenKavanagh, and this is my final year project presentation on the project OpenHab in Electrical Community Grids. The layout of the presentation is as follows. A background section will give an overview of the project. The aims and objectives of the project will then be listed. A literature review section will detail the technologies used within the project. The design of the system will then be explained. How this design was implemented in the final solution will be detailed. The results of testing the final system will be analysed. The conclusions of the project and any future work will then be summarised. A research project is currently ongoing in TUD's research department. This project is known as the Community Grid, and it looks at minimising electrical disturbances in the grid system caused by microgeneration. This microgeneration could be from solar panels on the tops of houses, for example. When too much power is generated, this can lead to disturbances within the grid system. The solution this project looks at is developing a control loop which detects when too much energy is generated and then consumes this excess energy back within the community grid. In turn, then, this reduces the disturbances caused by microgeneration. To design the control loop, a list of sub-objectives were created. First, the OpenHab application would be installed on the Raspberry Pi. OpenHab is a free open-source software which is used to manage smart devices within a home automation network. The sensory devices within the system are smart meters which record power readings. The smart meters in the project use Modbus TCP/IP communication protocol. The devices that are controlled within the project are smart plugs. The smart plugs use the Z-Wave communication protocol. A remote database will be configured which is not stored locally on the Raspberry Pi. This database will hold power readings from the smart meters and other information on the devices in the network. The control loop will then control the smart plugs based upon the power readings stored within the database. The system will then be tested and the real-time characteristics evaluated. The goal is to have a loop time for the control loop of 250 milliseconds or less. The literature review section looks at the technologies used within this project. OpenHab stands for Open Home Automation Bus. It is an open source software that can be installed on Linux, macOS, and Windows systems. The function of OpenHab is to manage smart devices within a home automation network. Smart devices are connected to the Smart Hub through physical ports and antennas. In this project, the hub is a Raspberry Pi. OpenHab manages the resources of the hub's hardware to make these connections possible. The smart plugs used within this project are the AOTech Smart Switch 6 plugs. These plugs can be controlled on and off wirelessly. They also read values of voltage, current, energy, and power. The communication protocol they use is the Z-Wave communication protocol, which is standardized by the ITU. Z-Wave operates at 868 MHz. This is an advantage in the home setting as it avoids the 2.4 GHz frequency for home Wi-Fi. Z-Wave devices form a mesh network shown in the diagram here. This is an advantage as if one Z-Wave node cannot directly reach another node, packets can be forwarded through intermediate nodes. This means increasing the number of devices in a Z-Wave network also increases its range. The meters used for this project are the PM3112 Modbus TCP meters shown here. The meters require a voltage and current reference. The voltage reference is obtained from a live and neutral wire from a wall outlet being connected to the V+ and V- pins on the meter. The current reference is obtained from a current transformer which clips onto the outside shielding of a live wire to obtain a current reference. From these voltage and current reference values, power references and power values can be calculated. Modbus TCP/IP is the messaging protocol used by the smart meters. TCP sits at the transport layer of the OSI model. It is used to ensure secure communication between devices and error checking in messages. IP sits at the networking layer. This is used to ensure packets are routed to the correct destination through IP addressing. Modbus is at the application layer, which defines how data is interpreted by the protocol. The The next section details the design of the system. The system stack was designed to show the components of the system. At the bottom of the stack are the smart plugs. These plugs are communicated with the hub using an OpenHAB binding for Z-Wave. A binding is a software package within OpenHAB that enables communication to devices. OpenHAB items represent the functionality of devices configured in OpenHAB. For the smart plugs, the main items used are on-off control. The functionality of these items is communicated to the device through channels. OpenHAB has its own programming language, known as the OpenHAB rule system, which can be used to implement control logic. The rule system uses the cron scheduler to execute jobs. The fastest this scheduler can execute jobs repeatedly is every second. This will not provide the control loop time of 250 milliseconds desired. Sitemaps are front-end user interfaces OpenHAB provides. OpenHAB also has a pre-configured web server installed with it. The web server has a REST API where external programs can access OpenHAB devices through HTTP requests. This can be used to bypass OpenHAB's rule system. Python was chosen to develop the control loop as it provides all the functionality required and prototypes can be developed quickly. The smart meters can then be directly accessed by the control loop. The database can also be directly accessed from Python to log and query values. One of the main aims of the control loop is achieving a loop time of 250 milliseconds. In helping to achieve this, the system was designed to incorporate asynchronous programming and threading. Asynchronous programming allows code to continue to execute when a blocking statement is encountered. To show this, a comparison can be done against a synchronous operation. Code will execute in a synchronous operation up until a point where a blocking statement is encountered. In the system for this project, the blocking statements are requests sent to the REST API, an SQL transaction to the database, or a Modbus query to the meters. The system will now halt and not execute any further code until a response is received from a given request. Code will then continue to execute once a response is received. In the asynchronous implementation, when the blocking statement is encountered, the next task within the event loop is executed instead of hanging the system idle. This means that code will continue to execute. When a response is then received from the given request, the event loop goes back and continues along the same path of execution. Threading allows multiple tasks to be executed in parallel. The main tasks within the system can be broken down into individual components. Smart meters are queried to obtain power readings. The meter readings are then logged to the database. The database is then queried to obtain the most up-to-date meter readings. The meter readings can then be tested and actuation of the smart plugs can occur. If the reading is above a set point, the plugs can be turned on. If the reading is below a set point, the plugs can be turned off. These tasks do not all have to occur one after another. They can be divided into tasks to log data and tasks to control the devices, each executing on their own thread. The first thread can query the smart meters and log the readings to the database, while at the same time the second thread can query the database for meter values and actuate the smart plugs. There are 2 smart meters available for this project. 2 control loops can be configured using the 2 meters to test the system's behavior when 2 control loops are executing in parallel. Each of the loops can control 2 of the available 4 smart plugs. This section details the implementation of the system. The OpenHAB application was installed on the Raspberry Pi hub. The hub was connected to a network switch which had a router connection to allow internet access. The Raspberry Pi does not have a Z-Wave antenna, so instead a Z-Stick Gen 5 was used, which is a USB Z-Wave antenna. The smart plugs were then configured in OpenHAB so they could be controlled on and off. To obtain a current reference for the meters, the current transformers were clipped around the shielding of a live wire connected to a plug socket. 14 volts was supplied to power the meter on from a power supply cable. The voltage reference for the meter was connected using a live and neutral wire which were inputted to the V+ and V- pins. The smart meters were housed on a DIN rail, with the power supply and voltage references being connected to a plug socket. The current transformers to obtain a current reference were clipped onto the shielding of a live wire. Each meter was then connected to a network switch, which enabled communication to the hub. MySQL was installed on a laptop. The laptop was then connected to this network switch, which the Raspberry Pi was connected to enable communication. The final control loop incorporated all the individual components of the project. An OpenHAB rule was created, which executed once the OpenHAB application started. OpenHAB is configured to launch once the Raspberry Pi is powered on. The OpenHAB rule launched a Python configuration script. The configuration script then spawns 4 threads for 4 different Python processes. The first script creates a connection to a smart meter and queries it for power levels. It then logs these readings to the database. The second script queries the database that any of the available power readings which the meter supports, shown in the table, can be used to turn on the plugs. These 2 scripts were for one of the smart meters. Similar scripts were created for the second smart meter and executed at the same time. Each control loop controlled 2 smart plugs each. The scripts were then looped through continuously to complete the loop. Another OpenHAB rule was configured, which executed when one of the smart plugs changed state. This rule launched a Python script, which updated the status of the smart plugs in the database to either offline or online. This section details the results of the project. The average time taken from when a request was sent to OpenHAB to toggle a smart plug to when it actually executed was 947 milliseconds. The average rate at which the smart meters can be continuously polled is every 10 milliseconds. The average rate at which the power readings can be logged to the database is every 10.15 milliseconds. A power reading can be obtained from the database at a rate of 8.38 milliseconds. The control loop was then allowed to execute for 90 minutes and the state changes of the plugs plotted. If the voltage was above 230 volts, the smart plugs were turned on, indicated by the green dots on the plot. If the voltage was below 225 volts, the smart plugs were turned off, indicated by the red dots. The 5-volt hysteresis margin was introduced to stop rapid toggling of the smart plugs. Successful control of the smart plugs was achieved. This section summarizes the conclusions of the project. The original goals of the project are shown. OpenHAB was successfully configured on the Raspberry Pi. Communication to the smart plugs was achieved through Z-Wave. Modbus TCP/IP was successfully used in enabling communication to the smart meters. Communication to the database and logging of meter values to the database was achieved. A control loop was created which successfully controlled the smart plugs based on meter readings. The real-time characteristics are shown in the table below, with particular focus on the smart plug time. This time was recorded when the OpenHAB REST API was overloaded with requests and the smart plugs toggled on and off every cycle. In a real scenario, the smart plugs will not be toggled on and off this often. It is therefore concluded that a loop time of 250 milliseconds or less can be achieved. There is still more work which can be done. The goal of the community grid is to minimize electrical disturbances from microgeneration. Research must be done into what power levels these disturbances occur at. A possible area to research is the balancing market in the integrated single electricity market, in which services can be offered in to balance the grid. The control loop was developed in Python for this project. However, a statically typed language such as C or C++ could improve loop time. The smart meters and database had a wired connection in this project. A Wi-Fi connection should be tested with these components, which would recreate a more realistic scenario. This marks the end of the presentation section. A demonstration of the system will now be shown. The hardware of the system is shown. The smart meters are housed within this power supply box. Power to the meters is obtained from this outlet as well as a voltage reference for the meters. The current transformers are clipped onto the shielding of the live wire here. The database is housed within this laptop, but the smart meters and the database connect back to this network switch, which is also connected to the Raspberry Pi hub. The Raspberry Pi hub then has a Z-Wave USB antenna to communicate with each of the smart plugs. OpenHAB's web server provides a logger to print messages to, which can be accessed from a web browser. This logger was used to indicate when the control loop had started. This message is printed, which indicates that the configuration script within the control loop directory has been executed. This occurs when the OpenHAB application is first launched. The configuration script then spawned 4 threads for the control loop. 2 of the threads queried the meters for power readings and logged these meter readings to the database, while the two control loop scripts queried the database for power readings and actuated the smart plugs based on these readings. The logging scripts queried the meters for power readings. This was done by reading the Modbus registers within the meters for voltage, current, power, reactive power, apparent power, and power factor. These readings were then logged to the all values table and the meter values table within the database. The database has 5 tables in total within it. The meters values table stores the most up-to-date power readings recorded. The control loop is currently running. If the table is queried for a value of voltage, from the timestamp it can be seen that the table is currently being updated by the control loop. The all values table is similar to the meters values table, however a record of all the power readings ever recorded is stored here. Querying this table for its first entry shows that a timestamp was recorded on the 5th of May for the first entry. The hubs table stores information on the hubs within the community grid. Within this table are the MAC address of the Raspberry Pi hubs and the IP address assigned to these hubs, along with a location. The devices table stores information on the devices a given hub controls. This information can include the status if they are online and what communication protocol they are using. The items table then stores information on these devices. As these smart plugs can measure current, energy, power, a switch value to tell if they're on and off, and a voltage value, this is stored within this table. The control scripts then queried the meter values tables for the most up-to-date power readings for the particular meter. These power readings could then be tested to make a choice to either turn on the smart plugs or turn them off. The tablet shown is a front-end sitemap to control the given smart plug here. The control loop is currently running on the Raspberry Pi, however, and currently the control loop is telling this smart plug to turn on. If I try to turn off the smart plug through the app, it does turn off. However, the control loop is correcting for this, turning the smart plug back on. The final script in the control loop is executed when one of the smart plugs loses connection. Going back to the OpenHAB log viewer, OpenHAB is aware that Node 3 has changed from a status of online to offline, as there has been a communication error and the node is no longer communicating with the controller. It also notifies us that our script has executed, which will update the database. Going to the database, the last query showed that Node 3 was currently a status of online. Querying the database again shows that Node 3 is now offline, as there's been a communication error and the node is not communicating with the controller. The testing of the system was divided into control loop tests, smart meter tests, database tests, and smart plug tests. The output of these tests was generally CSV files with timestamp information when a response was received from a particular component. These files could then be read into Python scripts and plotted, analyzing the different response times of the system or any other characteristics. Thank you all for listening, and I welcome any questions within the interview section.